That is one very important thing you need to know about linked data structures. Node objects are accessible to programmers only through variables. Since nodes link to other nodes, we don't bother to keep variables around for each and every node. This also means that if you do not implement your linked data structures carefully, you may have a node that becomes permanently inaccessible. If that happens, Java's garbage collection will come along and reclaim that memory space. Sometimes you want this to happen, like in the case where you're permanently deleting a node, but sometimes you don't. Let's look at what happens to the linked list when we add and remove elements. We'll start with the remove operation for list. Assume that the abstract list looks like it does at the top left corner of this slide, and its linked list representation is what we have here on the right. Suppose we want to remove the element at index 4 from the list. I'll give you 5 seconds to tell me what the element at index 4 is, starting from now. If you said E, you are correct. Remember that Java lists, just like Java arrays, begin with their first element at index 0. Therefore, our final list should have the E element removed. To remove an element from the linked list structure, we need to do the following. First, we need to find node 4. Then, we need to redirect all the appropriate links. And finally, we need to delete the node we're removing. Finding node 4 is done with the same technique we talked about when we discussed printing the list. We create a temporary node variable and we iterate or update that variable by having it follow the links. But wait a minute, there are two sets of links here. There are the next links and there are the previous links. Which links should we follow? I'll give you 5 seconds to decide, starting from now. Okay, I hope you can see that following the previous links is going to get to the correct node sooner. That's one of the nice things about a doubly linked list. If the index is in the first half of the list, you can follow the next links. But if the index is in the second half of the list, the previous links will get you there faster. Naturally, if you follow the previous links, you'll have to count down, starting from the last index, instead of counting up. The next step is to redirect the links around the node you want to remove. And in this case, there are 2 links that we want to redirect. If I give you 10 seconds, can you tell me which links we want to redirect? Tell me which node they're coming from and which link, next or previous, needs to move. And also, figure out where that link needs to go. 10 seconds starting from now. Ready? Because we are removing the node containing E, we need to take the next link of the node containing D and redirect it to the node containing F. Likewise, we have to take the previous link of the node containing F and redirect it to the node containing D. And that's going to look something like this. Now that looks pretty simple, right? Well, conceptually it is. But how do we actually do that in the code? For example, suppose I had a temporary variable pointing to the node containing E. How do I redirect the next node of the node containing D to the node containing F? Well, it turns out that you can do this with a single assignment statement in Java. But before I tell you what that assignment statement is, please pause the video and try to figure it out for yourself. Ready? This one's a bit challenging, but I've asked the question in this particular way to help us create the assignment statement. The question here says that we want to redirect D node's next link toward the F node. Of course, when I say D node, it's just shorthand for the node containing D. And when I say F node, it's just shorthand for the node containing F. Okay, so I'm going to write what we want to occur in an abbreviated notation. We want D node's next link to be redirected towards F node. The only variables that we as programmers have to work with here is the temp variable. Now, if I give you 5 seconds, can you tell me how to express the D node in terms of the temp variable? 5 seconds starting from now. Well, temp is just a variable name for enode, and enode's previous link is dnode. That means that temp.previous is our programming way of referencing the dnode. Similarly, temp.next is our programming way of referencing the F node. So we can tweak the statement we just wrote to say temp.previous next needs to be temp.next. So we've just replaced the D node with its programming representation temp.previous, and we've replaced F node with its programming representation temp.next. And now we're very close to being done here. Since we want D node's next link, we just use temp.previous.next. And since we want it to equal F node, we simply assign it. And that simple but carefully thought out assignment statement is all we need to redirect D node's next link to F node. I know that some of you may still be staring at this and saying, what the heck is Dr. K talking about? But trust me, once you get some practice writing this kind of code, it becomes, it may not ever become easy, but assignment statements like this will start making sense to you. Let's pick up where we left off. We had redirected the appropriate links, and now we just need to delete the node containing E. However, in the actual remove implementation, there is still one thing we have to do here before we can delete the node. As specified, the remove implementation will not only remove the element from the list, but it'll also return it. So if we're going to be true to the specification, we have to return the contents of the node we're deleting. But that's actually pretty easy. If we have a temp variable pointing to E's node, we just return temp.element. And when we return from the method, everything is taken care of for us. The temporary variable that was local to the method is gone, so the node we wanted to delete is no longer accessible. You can't access it through the header variable because we've already redirected all the links away from that node in step 2. Therefore, Java's garbage collector will eventually come along and it'll see that the portion of memory containing the unwanted node is no longer accessible by the programmer, and the memory will be reclaimed. And in case you missed it, there's one other change that we had to take care of before returning from the method. Any idea what it is? It's minor, but it's important. We have to modify the size variable because there are now 5 elements in the list instead of 6.